Let's do our first proof of the class. It's a fairly simple problem. Prove that the sum of any two odd numbers, meaning integers, not arbitrary real numbers. When we talk about even and odd numbers, we're talking about integers like 1, 2, 3, 4, 5, 6, etc. Also 0, also negative whole numbers, you might say, -1, -2, -3, -4, etc. Those are integers. Prove that the sum of any two odd numbers is an even number. How do you go about the proof? Abbreviated PF for proof here. You should write sentences, okay? It's not like geometry where you have like the statement reason charts. We don't want to do proofs that way. We do want to write sentences. It's fine if you use abbreviations. It's fine to use symbols, abbreviations, that kind of thing, to make your writing less, you might say, but they should be complete sentences. So you might start off with something like this. Let m and n be any two integers. Now I could write the words be any two integers, but I also could say that these are elements of z, and you make the symbol for the set of integers in kind of a fancy way like that. Why? I think it's German. Z stands for Zahlen in German, which is basically a word for number. Numer is another word for number. So I think it's a German thing, but we will use it a lot in this class. This is shorthand for saying, let m and n be arbitrary integers. Let m and n be elements of the set of integers, is what this means. That are both odd. We're trying to prove that if I've got two arbitrary odd numbers, the sum must be an even number. So I need to assume in my proof that my two numbers are odd, and try to show that their sum is odd. Now you could write down on the next line, we must show that m plus n is even, I meant to say. That's fine. It's not necessary. It might be helpful. I won't mark it wrong if you write that, but it doesn't really get you very far in this case, because it's like, well, what do I do with that? And that's common in proofs. You kind of get stuck. One big thing to think about when you get stuck is, have I used my assumption? In this case, have I used my assumption that they're both odd? And what does it mean to be odd? That's another thing you got to use, is what does it mean to be odd? What does it mean to be odd? Somebody tell me. Yeah, if m or n, if m and n are odd, they are 2 times some other integer plus 1. If they were even, they'd be 2 times some other integer, but they're odd, so we have to add 1. You could also, instead of adding 1, you could also subtract 1, or add 3, or subtract 17. It's simplest to think of it in terms of adding 1. There exists some other integers. Oh, so many fun symbols in math. Backwards E means there exists. Isn't that fun? There exists some other integers. What should we call them? Well, don't call them m and n. Oh, I don't know, s and t. They are integers, so they are elements of the set of integers, z, such that I abbreviate st. There's lots of such that's in proofs. Other people will abbreviate this in a funny way. They will do a backwards element of, but I think that's a bit confusing. So I typically use just st for such that m equals 2s plus 1 and n equals 2t plus 1, right? S and t are not necessarily the same, because m and n are not necessarily the same. It is important that we're doing this in the abstract. We're proving this for any two odd numbers, that their sum is even. That's a sentence. That's fine. I don't mind if you start sentences with the word then. So I capitalize my then. I don't mind it. Maybe it's technically not right, but I don't mind it. Adding gives m plus n equals 2s plus 1 plus 2t plus 1. Notice I'm using parentheses. Is that absolutely necessary? I think it's a good idea here, at least at the beginning of the course, to do that. To emphasize that I'm adding these two quantities. And then also emphasize, hey, I can get rid of the parentheses and rearrange by some properties of arithmetic that we know. I can, write this as 2s plus 2t plus 1 is 2. Why? You could just say because of properties of arithmetic, because of properties of integers. I'm going to be a bit more specific. I'm going to say because of the associative, it's probably good to get in the habit of saying this here at the beginning of the course, associative and commutative properties of addition in the integers or on the integers. I'll say in. Sometimes it's unclear whether you should say on or in. The associative property in this context could be thought of as effectively saying we can get rid of the parentheses. And more formally, when you use the associative property, it's emphasizing that this kind of thing is true. A plus B plus C in parentheses equals A plus B in parentheses plus C. The parentheses emphasizing order of operations. This is not part of the proof here, by the way, it's just a side comment. When you think about this expression, you say, okay, B plus C is in parentheses, so I add B and C first before I add A. When you look at it this way, you say, okay, I add A and B first before I add C. And the associative property says it doesn't matter. You'll get the same thing. So what that also means is you can get rid of the parentheses. I could also write this equals A plus B plus C without parentheses at all, because it's not ambiguous. You can do either addition first. That's the associative property. The commutative property, more formally, is that A plus B equals B plus A for any integers A and B. Yeah, I did rearrange. I brought the 2t to the left and this one to the right. Are we done? Did that prove it? Does that prove m plus n is even? Almost. What last thing should I do here? Factor out of 2, yeah. What does it mean to be even? It means you're 2 times some other integer. I got m plus n is the sum. I want to write it as 2 times some integer. It's really by the distributive property that I can factor out of 2. By the distributive property in Z, m plus n equals 2 times in parentheses s plus t plus 1, where s plus t plus 1 is an integer. I'm being extra picky about reasons here. By the closure property of Z. What's closure? It means when you add 2 integers, you get an integer. That's closure under addition. There's also closure under multiplication. When you multiply 2 integers, you get an integer. So I've proven m plus n is 2 times some integer. That means m plus n is even. 3 dots like that means, therefore, that's a fine shorthand. M plus n is even, and we are done. QED is Latin for quad erat demonstrandum, I believe I'm saying it right, which basically means I've demonstrated what I set out to demonstrate. If you believe in God, you can also say praise the Lord, PTL, or put a smiley face. Lots of different things you can do there. Actually, you'll often see mathematicians put a box at the end, or maybe a box that's shaded, or maybe two lines. There's lots of things that mathematicians do to celebrate the end of a proof. Right? We want to celebrate. We're done. At least we think we're done. By the way, I should say the distributive property, what is that as well? These associative and commutative properties are just with respect to addition. The distributive property relates to multiplication as well. It says that A times B plus C, in parentheses, meaning do B plus C first, then multiply by A, is the same as A times B plus A times C. And when you write that, you really mean do the multiplications first before adding, because multiplication comes before addition in order of operations. The integers do form an example of something called a group under addition. Group theory is our main topic for the first 2 months or so of this course. Z forms a group under addition. In fact, something called an abelian group under addition, fancy name. It does satisfy the associative property. Also closure, adding any two integers gives you another integer. There is something called an additive identity. An element, an integer, such that when you add it to any other integer, you get that other integer. What do you think I'm talking about? Big hint? Not okay. 0. 0 is the additive identity. And also there are additive inverses. What's the additive inverse of 5? Negative 5. It's opposite. Why? Because 5 plus negative 5 is 0. Should I say 5 minus 5 is 0? Not yet. We're not doing subtraction yet. Say 5 plus negative 5 is 0. 7 plus negative 7 is 0. Negative 17 plus positive 17 is 0. And it is commutative. That's why it's also what I said, abelian. Z actually also forms what's called a ring under addition and multiplication, where there's two operations, addition and multiplication. And it does have to satisfy, for example, this distributive property to be a ring. Ring theory, that's 2 months from now.